Welcome to Unit 10, the penultimate unit. In this unit, we're going to be talking about electric potential energy. And I wanted to start kind of with the big overview of electricity. We've done two parts of this, or at least part of a part. Anyway, we've done some electrostatics with electric field and electric force. And then we did some DC circuit stuff with resistive elements. Now we're going to go back to electrostatics and look at electric potential energy and electric potential and how voltage, which we talked about in circuits, is derived from charge distributions. And then we're going to look at some circuit elements like capacitors that require this understanding. And then in Unit 11, we'll get into electromagnetism, right? We know electric force and electric fields, how they're related. And we are going to start today with electric potential energy. We're going to make the connection to potential and potential difference. Same thing we've done before. We're going to have point charges or simple arrangements of charges and continuous charge distributions. With circuit elements, we have batteries and resistors that we've already done. And I mentioned this, I think, in class the other day. There's going to be capacitors, and we're also going to look at inductors, but that's not until magnetism. Electromagnetism, we look at magnetic fields, which gets the symbol B, and how that affects charged particles and moving charged particles. Maxwell's equations is the final piece to electricity and magnetism, where we combine the relationships between electric field and magnetic field and how changing one affects the other. That'll be very much at the end, and that's not something you actually are responsible for doing, but it is kind of the culmination of all of this. So we already know these things. We already know that we can use Coulomb's law to figure out the electric field and the electric force for point charges. We can use Coulomb's law and integrate to do that for distributed charge, and for highly symmetric arrangements, we can use Gauss's law. And so what we want to do now is continue this in talking about energy and potential difference for various charge arrangements, right? The big thing here is to link the electrostatic stuff we talked about to the circuit stuff we've been looking at, and make sure we understand how they can be connected. So in this video, we're going to specifically look at electric potential energy for various arrangements of charge. And the way you want to think about this is if you imagine taking two charges, and you can place the first one in empty space without having to push against any electric field. But then if you bring another one close, you have to do more and more work the closer they get. And holding them there, right, bringing them together, caused it to have some amount of potential energy, which if released, they would fly off and have kinetic energy, right? It would be converted into kinetic. If these charges are opposite, we could have negative potential energy. That means to keep them from smashing into each other, you're actually doing work pulling them apart. So that's positive work to separate them, which means negative work to bring them together. So you might ask yourself, if we bring two negative charges together, is this going to be positive or negative? And so we use the analogy that if you have to push them together, it would be positive work. If you have to pull them apart, it would be negative energy, and you do have to push them together. So this is positive potential energy. So in summary, if you have two like charges, you put them together, and that has stored positive potential energy, electric potential energy. If you use opposite charges, you get negative. And so you can just multiply the signs, and that will give you the correct sign for potential energy. So this is kind of the basic idea. And this is where it's very similar to gravitation. The potential energy of a system of fixed point charges is how much energy you had to use to put them in that arrangement. Now, with gravitation, we said that when things were infinitely far apart, it had zero gravitational potential energy. And we're going to say the same thing here. The big difference is that, the big difference here is that we could have either positive or negative potential energy, unlike gravitational potential energy, which was always negative. So when we thought about gravitation, you lift something up to infinitely far away, and you can figure out how much potential energy there will be, right? The work you have to do is equal to the force you apply times the distance, and that force has to be equal at minimum to the gravitational force. And so you can find this work by integrating from r out to infinity to figure out how much work it would take to pull it apart, right? GMM over r. And since we call zero at infinity, this is a negative gravitational potential energy of negative GMM over r. And so that's the summary of what we did with gravitation. Now, what about electric potential energy? Well, if you take a positive charge as your central charge, and you have a negative charge that you're sort of moving around, you might predict that the same thing would happen. This would be very much like gravitation. You're applying a force that has to be equal and opposite to the electric force in order to keep it moving away at a constant speed. That force goes like K Q1 Q2 over R squared, very similar to the gravitational force. If you do the integration, you end up with K Q1 Q2 over R as the electric potential energy at a particular point. And this time, we really want to make sure we want to use the signs, because two positives or two negatives will give us a positive value here. One positive, one negative will give us the negative sign. So this formula, which is very much like the gravitational potential energy formula for universal gravitation, is for 2-point charges only. This is the energy to put those two charges close to each other. It's a scalar. It can be positive or negative, and it's zero when it's infinitely far away. They're infinitely far away. And the signs that you get will tell you, when you plug in the charges, will give you the correct sign of the electric potential energy. So for example, here's an example problem. An electron and a proton are 1 angstrom apart. What is the electric potential energy? K Q1 Q2 over R is our formula. And we have 9 times 10 to the 9th for our K value, and 1.6 times 10 to the negative 19th coulombs, positive and negative for our two charges. Angstrom is 1 times 10 to the negative 10th meters apart. We get about negative 2.3 times 10 to the negative 18 joules. And this is the electric potential energy of that particular arrangement. What if you have more than two charges? You should remember this from gravitation. You have to figure out the electric potential energy for having 1 and 2 next to each other, 1 and 3 next to each other, and 2 and 3 next to each other, because each of them would affect the other. So that's how we would do that one. It's the scalar sum of all the possible pairs, so we can do the calculations, and the total is all of them together. Another example here that you can do is you can talk about something like this. A conducting sphere of radius r and charge positive q is set on an insulated stand. Charge positive q is released from its surface. How fast is that going when it's a distance of r from the surface? Can we use second law in kinematics here? No, acceleration isn't constant, so we need to use conservation of energy. Is the easiest way to do this one for q released from the surface. So we're going to start with kinetic plus potential at the beginning equals kinetic plus potential at the end. No kinetic at the beginning, right? Because it's at rest. So K final is the difference in the potential energies from the surface to the outside. At the surface, you have KQ over R. And then at the new point R from the surface, that's a distance of 2R from the center, you get KQQ over 2R. You get V final as the square root of that. And you could, plug in an actual value if you knew it. What about at the center of a ring of radius r and a total charge positive q? Now this one, you're probably tempted to say 0. But because it is not a vector, it's not like we have forces pushing in all the different directions or electric fields pointing in all the different directions. All we care about is how far we are from all the charge. And in this case, it's pretty simple. If you're at the center, little q is a distance r from every bit of charge. And so the electric potential energy is KQQ over R, right? And if you want to think about this, if you start with a ring of charge and you have Q way out there and you bring it in, you're going to have to do positive work to place it at the center of that ring. That center of that ring would actually be an unstable equilibrium. If you got it just right, all the forces would balance out. But if you knocked it a little bit, it would fly off to infinity. What about a semicircle? Well, the same basic idea applies, right? It's KQQ over R, negative, right? Sorry. And because they are opposite charges, very simple, right? It doesn't matter about the electric field or the electric force in this case, because we're just interested in how far away is that charge from this point. And because it is symmetric, we get a simple answer. Right? The big idea here is that we're treating this a lot like gravitational potential energy. The biggest difference between these two is that this can be both positive and negative instead of just negative like the gravitational potential energy.